Yeah, so I will talk a little bit about our work on measuring resilience. So if you look at literature, especially in the power domain, everyone is motivating smart grids, microgrids by the need for more resilient grid infrastructures, right? And the question we were asking ourselves was, what does that actually mean? So usually, when you talk about resilience, or if you read related work about resilience, more resilient grids, then it's always about weather events. That's the big thing usually. So if a tree cuts a line, how much consumer load can I not supply anymore? And the better this ratio is, the more resilient I am. And if I can control this more intelligently, then my grid is more resilient. But we're looking at this into a little bit more detail and looked at how can we measure resilience in a more general sense. So we can also incorporate things like cyber attacks and more generic challenges to our grid infrastructure. So in my case, if I'm the first, because I'm the first one in this 2 tracks about resilience, it's good because I have the possibility to define it any way I want to define it, right? So first, let's look at some definitions for resilience that we find in the literature, right? So we want to maintain state awareness and an operational level of normalcy when we have unexpected and malicious challenges. Or, no, wrong direction. We want to mitigate most undesirable incidents, or we want to minimize the adverse impacts if we cannot mitigate them. And in the last case, we can recover if we could not do the first 2 things. So that would be another definition. Or more power grid specific, we want to maintain continuous electricity flow and respond to the cyber-physical challenges in real time or near to real time. So if we think about these definitions, and there are a lot more throughout the literature, then what we come up with is that we're actually talking about something that looks a little bit like this, and I will explain this diagram a little bit further. But in general, very generally speaking, if we talk about resilience, we're talking about something that defines performance over time. And then, depending on how our performance evolves over time, that's how we can measure resilience. So what we see here is basically we have the blue curve up here is our performance of our system, and the red curve down here is, let's say, our abstract challenge to our system. And then we can define a lot of thresholds and parameters here. For example, we can define sort of a threshold at which, if the challenge exceeds this threshold, our system strongly degrades in performance to a certain level here. And then at some point, it might recover again. And depending on how this performance behaves in response to the challenges, that's how we can, to some extent, measure our resilience, right? So if you look at this, this looks not too complicated. But obviously, the question is, what do we define as performance and what do we define as challenge? Because depending on from what perspective you're looking at your grid, you might define your performance differently. So if you are in the, I don't know, accounting department of an electricity provider, performance means something very different to you than for the operations manager or for the technician who goes to the field and repairs some device units, right? So this blue curve actually is not one curve. And the red curve, if we consider all types of challenges that our smart grid or cyber-physical systems is challenged by, this is also not one curve. So the whole thing gets much more complex, but this is just the simple thing that we can see, right? So if this is resilience, then we can classify resilience by 3 potentials. And that's not defined by me, but by some related work. So they define 3 potentials that we can use to measure resilience, and this is called the absorbing potential here. So if we always have some level of challenges, and we want to know until which level we are not degrading severely, right? So that's how much challenges can I absorb without degrading. The second one is survivability. So whenever this threshold is surpassed, then I don't want to shut down completely. I want to maintain some sort of controllability. And then the last thing is recoverability. So how quickly, if this threshold is exceeded and I'm degrading, how quickly can I come back to normal operation? How quickly can I recover? And these 3 potentials basically define or encapsulate how resilient my system is. So we can have a very robust system. If we are completely robust, that's perfect, but usually there's a trade-off. If we are very robust, then we are not very recoverable. So whenever something really goes wrong, it's very hard to recover afterwards. So there is sort of a trade-off. And then we always have malicious challenges or random challenges like weather events, right? So we want to cover both in our metric. So how do we define resilience if we want to measure resilience, right? And the way we defined to measure resilience, our metric is, on first glance, a very complex formula, but it's not very complex. Basically, it's the ratio between the blue area and the green area. That's all we need to know. This is always between 0 and 1, obviously, because the blue area, if we have complete, so this is the lowest level of performance. This is basically the complete shutdown of our system. So a system can never decrease more than completely in performance. So it can never be bigger than the blue area. That would mean the resilience is 0. And if the less we degrade or the faster we recover, the smaller the blue portion with respect to the green portion is, and the more resilient we are. So that's easy to grasp, and that's also something, if we define one performance measure, we can immediately measure our system, and we can measure how resilient it is in real time. We just say, how much voltage do I lose in this time frame under these challenges, and that's how we measure our resilience, and we are basically done. But that's not very helpful if we want to design a system, right? Because we cannot measure it while we're designing it. And it's also a little bit of a simplification of the whole system. So instead of looking at only one performance, we see that we define resilience with respect to PI, which is one performance indicator. And performance in itself is a vector of multiple performance indicators. So instead of looking at one of these PIs, we want to see how they correlate. So if one performance goes down, that usually means that another part of the performance also goes down in response to that. So when we define one performance indicator, if we can define the relationship between the performance indicators, we can basically measure the resilience with respect to all of them, always in the same way. So this formula always stays the same. It's just a matter of which PI do I put in here, right? So that's that. And then how do we measure, what are these PIs? And in mathematical terms, it's basically a lot of differential equations, because we want to see the response of one curve with response to the others. And this also looks very difficult, but I will walk you through it. So that's our performance indicators in the next, so the differential part of the performance indicator, right? So then the first term of this equation is the recovery potential. It's quite easy. It's the positive term of the, so if the curve goes in the positive direction, that's how quickly we recover, right? And it depends on a couple of factors. So we have time, we have how quickly it's specific to the performance indicator, some recovery constant, or it could be also a complex term. The current performance, so if we are in a low performance level, we might recover faster because the last 5% might be more difficult, or the other way around. And some nominal performance. We can never operate better than nominal, right? So that's some equation that we recover. And then there's an absorbing potential, which is the negative term. So it depends on time again, right? And then a vector of disturbances plus my current performance. And the last term is some survivability. So at what point do I never recover again? So once the survivability passed, I'm always staying at the lower level because I cannot recover out of my own energy. So basically, if we model resilience, then we can model it by a set of these differential equations where the level of challenges to my system can actually be defined by the other performance indicators and external challenges. So this vector of challenges can be external challenges or internal challenges that come from other performance indicators. Now, that was very abstract, so let's go down to a concrete example and see how this would work out and what the response, what this would look like, right? So we instantiated this concept in a microgrid use case, right? And the microgrid use case, microgrid is basically a small portion of a grid that you can isolate from the main grid, and then it works independently for a certain amount of time, and then you could reconnect it to the main grid, and it can draw power from the main grid or supply power to the main grid. And one problem with microgrids is that at some point you need to reconnect them, or you need to disconnect them. The disconnection part is fairly easy, let's say, but the reconnection part is difficult because you need to bring the two systems in sync. So all the power parameters need to be synchronized before you reconnect, otherwise it's very difficult for the physical equipment to stand this, right? So in this reconnection part, we want to level the frequency and the phase of the system, right? So if we see this, so this is our microgrid part, and then there is a host grid, so the main grid, and then there's some communication network where we get some measurements about the state of the microgrid from here, and about the state of the main grid from this PMU, which are some measurement devices. And by combining the two, we can use a simple controller, like a proportional integral controller, and try to minimize the error between the two systems, right? And if it's close enough, we can safely close the circuit breaker, and the two systems are connected again. And when we're disconnecting, then we need this communication in order to reconnect them. So that's our setup. And now we basically consider our system. And in general, we say a cyberphysical system comprises of 3 domains, right? There's a physical domain, a cyber domain, and some level of control domain. It's also often called cyberphysical domain in related work or similar. So basically, to have the full system, you need some sort of integration between the cyber part and the physical part, and that's usually done in the control part. So when we run our whole system, we model 2 external challenges. So one is a change in load in my microgrid. While I'm synchronizing, the load changes. So this changes also my frequency and my phase. And therefore, this is a challenge to my controller. So we see that there is a challenge to the physical system, and that poses a challenge to the control system in response. So that would be one of these C's in this C vector, in this challenge vector. It would come from here to the physical system, but then would be abstracted on how it affects the control. And then a second attack is a cyber attack. That's, in our example, we use some sort of simple denial of service attack that introduces a network delay. So the delay of our system would be a performance of our cyber domain. If you just look at cyber, we would say, how well is our network performing? So how big is the throughput, or how much is the delay in our packets? So we can measure this as a performance of our system, but it's also a challenge to the controller again, right? So if there is a big delay in my communication, it's harder for the controller to respond in real time. So here we see how these performance indicators of the system also affect other performance indicators of the system. And then at the end, we want to look at the phase error, at the frequency error, and at the settling time of our controller. So those are the performance indicators that we actually want to measure in order to measure our resilience of our system. But we cannot, it doesn't make any sense to we can measure those. We can just plug in some measuring device and measure what the frequency error is, and that we can measure the resilience. But if we don't model the whole system, we don't know where we can improve our system. Because I cannot improve the phase error response without knowing where the delay happens. And the delay happens because I have a cyber attack, I have network delay, I have a load change. And if I don't know this, then I cannot improve my system. So that's why we model it like this. I spare you with any more maths. So we implemented this as sort of set of differential equations and modeled this in a MATLAB simulation. And this is just an overview of how this looks. So basically, if you measure this thing in real time, you would get, at first you would measure the load change, right, which is a step change. There is some load here, and at the end it's up here. So there is the physical load step is in the dashed line, right? It looks like this. And because we cannot really model indefinite gain in a differential equation, we approximate it by this curve in our model. So that's the first step. And then we can model the frequency error, which is basically traditionally, so if you just measure it, it starts oscillating like this. So it oscillates about around the point where you want to have it, right? You have a reference signal, and the frequency starts to oscillate around it because the controller tries to minimize the error. So at first the error is very big. It needs to decrease the frequency. At some point, it realizes that it reached a point, but it's still going down, and then the controller realizes, okay, I overshot my goal. I have to get back up, and that's why you get this sort of oscillation. But we are only interested in the negative impact. So we are only interested, we see a challenge is always negative from the nominal performance. You cannot be better than nominal. So that's why we just flip this original measurement downwards, and then you get this green measurement. So it's just, that's the cap, and we just flip everything down. So that's this. And then we can actually estimate it again. So basically, we then just say, OK, we don't want to write the differential equation that's describing this oscillation pattern, because we are not that interested in the exact number of oscillations or the exact curve. We're just estimating it by this red curve. We lay it over it, and that's how we measure our frequency. And then we do the same for the phase error, right? So we have the phase error, we flip it down, and we estimate it by another curve. And the red area here, that's how we measure our resilience. That's basically the final performance indicator that we are looking at. We want to know how quickly do we get our phase error in an area where it's OK to reclose the circuit breaker. And how long are we? How long does it take to get to this settling point? This is TSP. It's the settling point of the frequency error. And the reason why this is drawn like this is because obviously the phase depends on the frequency. So there is a dependency between the frequency and the phase. So from the load step impacts the frequency, and because the frequency changes, the phase error changes, and that's what we are finally interested in. So there you see again how this steps through. And you can draw the same figure for the network delay again. I spare you that one. So this curve is impacted by the frequency and by the delay of the network communication. So we have this, and now we have basically a model of our system. And with that model, we don't need to run the simulations for each load step and for each network delay. We can just simulate it because we have a mathematical model, and we can just import different parameters and see how the resilience of our system would behave. So basically, instead of having a load step from L0 to LS, we can now put in real numbers, and we get a measurement for resilience for all of these load steps and also for different network delays. And that's useful because then we can compare different systems, right? So let's try and do this, and we get a curve like this. So if you remember the initial curve, we are integrating this curve basically from here to the settling time, which is the red curve then. And that's basically then we compare it to the maximum of performance degrees, and that's our resilience. So it's always between 0 and 1, we know that. And we see that this is basically the load step. So as we go down, we introduce a different load step. So the load step gets bigger, that means more challenge to my system, right? So we expect with more challenge that somehow the resilience changes, or it's not changing, right? And then we introduce different network delays in our system, also just to see how the response is to different network delays. And this is quite interesting because in the beginning, if we have a small load step, we see our recovery potential. Because with the small load step, the frequency is not changing that much, and that's why the phase error is not big enough to hit its maximum. And that's why this is more or less a linear degradation. So to some extent, at some point, we reach a linear degradation, and then we hit this point where our recovery potential, or absorbing potential is used up. And then only the recovery potential counts. And this is more or less static. We see that it's more or less always the same, unless we introduce different network delays at different times in our run. And that's weird. And the reason for this is because we are integrating over different parts of our system, right? If we have a smaller challenge or a smaller network delay, then we are recovering faster, and we stop integrating here. So the base square gets smaller as well, and that's why we always have sort of the same resilience. Unless we use different delays in the middle, and then this curve gets different, and then we have a different ratio. So instead of using each one independent, and that's my last slide, we can integrate always over the longest time frame. So the one that finishes last, the one curve that gets the settling point at the very last point, that's the one we use as the time we integrate over. And then we get a little bit of a nicer curve, what we would expect. So basically, if we want to compare these systems, we can basically say they always still have this linear degradation until they use up their recovery potential, which is at the same load step point, more or less, because it's only depending on the load step. But then we see that the network delay actually affects the resilience quite a lot of my system, because the controller cannot handle this delay efficiently enough. So the more network delay we introduce, the lower the resilience of our system is. And that way we can compare different systems with such a metric. We can model all types of performance indicators, and we can then use it to compare the resilience of our system. We can also see where we can increase the resilience. So by increasing the absorbing potential or the recovery potential, which one is more effective, where is more to gain, something like this. Thanks.